All right, good people, welcome back. We are now going to figure out how to find an interval of convergence. So, what if my radius is not zero, meaning there's only one point where it converges, and that would be the center point? What if my radius is not infinity? That means that any x value would cause the power series to converge. What if my radius is an actual value? That means that the r, the radius, represents the distance from the center both to the left and to the right, kind of that, like the width of this interval. But what happens at the end points of that interval? We're going to have to test them separately for convergence or divergence. So, all those tests that we did in part one, we're going to use now in order to test endpoint behavior of an interval of convergence. So, we're going to start the way we normally start, and we're going to use the ratio test to help us out. We're going to take the limit as n approaches infinity of the absolute value of x to the n plus 1 over n plus 1 times, or really divided by the nth term, but we're going to multiply by its reciprocal. What do we want? We want this to be less than 1. In order for it to converge, the ratio test limit has to be less than 1. Can I reduce anything? Yes, I can reduce this with this. I cannot reduce this, however, so I'm left with the limit as n approaches infinity of the absolute value of x times n over n plus 1. Now again, this limit is only affecting n's, not the x, so I'm going to separate it. And I'm going to say I'm going to take the limit of this times the limit of this. Well, the limit of this part that has n over n is just 1 times this limit, and the limit of this is just the absolute value of x. So I'm left with the absolute value of x has to be less than 1. When is that possible? Oh, when I choose this interval. So if I were to draw this, I'm looking at an x values that start at 1 and end at 1. What's the center point? Oh, it's 0. Oh yeah, look, there's nothing. I'm not subtracting anything to the x, so therefore my center is 0. What's my radius? My radius, r, is 1 because the distance from 0 to 1 to this endpoint is 1, and the distance between 0 and the other endpoint is also 1. So it doesn't matter whether you measure it this way or this way, the radius is 1. So the radius of convergence is 1, but what about the interval of convergence? What happens at the endpoints? We have to check individually. So we come over here and we say, well, what if x equals negative 1? Then I have this negative 1 to the n over n. I have this series to check. And then what if x is equal to positive 1? Well, then I have this series to check. Yes. Well, these series should look familiar. This one especially, 1 to the n is just 1, so I can rewrite it like this. And that's the harmonic series, and that diverges. And if it diverges, that means we are not going to include not included in my interval of convergence. So we are guaranteed that any x value between negative 1 and 1, if I substitute it into the power series, original power series, is going to make it converge. What we don't know is what happens at the endpoints. We have to check them separately. I check the right endpoint, x equals 1, and that causes it to be a harmonic series, and that diverges, so I'm not going to include it. When I check this one, this is an alternating series. It's an alternating series that we've talked about. But if you remember the alternating series test, is the limit approaching 0? Yes. Is it decreasing? Yes. So therefore, this converges. This is the alternating harmonic we had done in a previous video, and it definitely converges. All right, so that means I'm going to include the left endpoint, but not the right. So my radius of convergence is r equals 1, and my interval of convergence. So this is telling me what are the actual x values that will make this power series converge. Convergence is negative 1 less than or equal to x but less than 1. That means any x value, including -1, but not including 1, and anything in between, will make this series converge. The radius just tells me the width of the interval where x values cause it to converge. The interval of convergence actually tells me which x values, including the endpoints, we've checked them, will converge. We're getting closer to something that's really neat, and that's going to be coming up in the next videos. And I'm a little excited to show you and how this connects to that. Notice we determine the convergence and divergence by using the rules, the tests, the types of series that we had studied before in part 1. Now we're introducing these ideas that we can have a power series and show that it converges for certain x values. And coming up in the next big idea is showing you how a power series can be equated to an actual function that you and I both know and use all the time. That's the excitement of what's coming up. In the next video, we'll show both part B and part C, and we'll do the interval of convergence. And then I'm going to go ahead and skip the differentiation and integration part because I'm really excited to get into the next unit topic, which is the Taylor approximations and polynomials.